by a transfer function. And here we have just chosen one pretty famous transfer function. This is the transfer function of a first order low pass. As it may be realized by an RC filter circuit. Corresponding differential equation looks like that. Y plus t by dot is x. So Laplace transform formulating down the transfer function will lead to x inside one box. Yet, and of course, we have, yes, before we started this calculation, we have had also a simulation with MATLAB Simulink. And then we could clearly see that there, at the output, we will have a superposition of a so-called Einschwingvorgang. Our transient phase here is the superposition with a eingeschwungener Zustand, with a steady state behavior. In steady state, the output looks also like a sinusoid with the same frequency, but shifted in time, and sometimes also with another amplitude. And we have read from our simulation those values here. And now the question is, hey, can we also do that on a piece of paper? And do that by analytical calculation. And, well, we have used our Laplace transform mechanism. And then we have found one pretty important fact. And this fact is, if you are only interested in the eingeschwungener Zustand, in the steady state response, then it's sufficient to set the S to j omega. Then what comes out is a transfer function which looks like that, 1 divided by 1 plus tj omega. And this contains all the information about the eingeschwungener Zustand. And this is, well, a little bit lengthy, that calculation here. And you don't have to be able to reproduce all that stuff here. However, you should keep that in mind, what is done here. And that says, well, you can obtain from this transfer function, given like that, 1 divided by 1 plus tj omega, you can obtain two informations, because that is a complex number. And a complex number carries two informations inside. One is the real part, the other is the imaginary part, or in this case, that is the important information, that is the absolute value and the angle. And the absolute value gives us what we call the gain, that is the ratio of the amplitudes, output amplitude divided by input amplitude, and the angle, that is the phase shift. And yes, and finally, we have formulated that recipe here once more. This is what you should keep in mind. So I will not ask you in the exam for calculating stuff like that here. That was only to derive this final result. But this here is an important thing here. Take the transfer function of the system g of s, replace s by j omega to obtain a complex function, and then obtain the gain by taking the absolute value and then take the angle to obtain the phase shift. Now we have formulated that exercise, and well, I got some solutions from your side. I think I have them on my computer here right now, and we may have a look inside. I think most of you found the solution. There are some small bugs sometimes, and this is what we now just want to discuss. What is the solution to that thing? Oh, by the way, yesterday there was a small beetle here on my paper, and perhaps you remember and that was totally shocked by that mathematics, and has not moved anymore. And now, in the meanwhile, the animal is identified. Nelson gave me the information. It is a ladybird, and I also had it identified. In German, it's Marienkäfer. And after the class, I brought this beetle back to the nature, to the outside. Okay, then it started to move again, because then the mathematics was not around it. Good, now let's, perhaps before we come to the solution here, I would like now also to have a look in our script. And I think I have sent that to you, and you don't have to print it out. I think it's sufficient when you have it on your computer and see at the end, there is something like mathematical basics. This is what we have discussed also so far here. Yes? And here, yes, just to show you what's all in the script, and you see the complexe Rechnung. That seems to be important. Yes, and a plus jb, real part of that is a, imaginary part of that is b, and it's stated here. The absolute value of that is, yes, a squared plus b squared, and the root out of that. And the next formula, and I have to make a note on that, that is not perfectly written here. The angle of the complex number is stated here, the arctan of b divided by a. Well, if you look at that drawing here, which is not the perfect drawing here, but there helps here a real part of a and imaginary part of b, and we often take such an arrow here, pointing from the origin of the coordinate system to the number here, and then that is the angle. And we are measuring the angle with respect to the positive real axis, and positive angles are done when we are moving counterclockwise. So from here we have in this case to move counterclockwise to then, yes, to that line here, to that arrow. And so here in this case, it's really true, the arctan of b divided by a, that is the angle. However, if this arrow is in another quadrant, here, let's say it is in the second quadrant, then this formula is no longer valid. This arctan just deliver us only values between plus and minus 90 degrees. However, those angles may also be 135 degrees, and then this formula is not absolutely correct. And so here I want to show you a MATLAB function, and you probably have heard of that, artan2. Yes, and the artan2, that is the arctan with two arguments, and we have to enter artan. The first number is the imaginary part, and the second number is the real part. And then this converts that correctly. And considering also in which quadrant the complex number is. I guess you have already heard about that function artan2, and it's also available in MATLAB. Simulink and MATLAB. Sorry, in Simulink we do not need that. Good. Coming back to our script here. What is an important formula which we will have also referred to already is that Euler's formula or Euler's formula. E power j alpha is cos alpha plus j sine alpha. And for some applications, we also may substitute, perhaps I'll make it a little bit larger, may substitute the alpha by omega t. And then e power j omega t is cos omega t plus j sine omega t. And if you think about, hey, where is that complex number? E power j alpha. Then this number is somewhere on the unit circle. Why? Because the absolute value of that thing here is 1. Real part squared plus imaginary part squared summed up and taking the root out of that, as then we have cos square plus sine square, and then, that sums up to a 1. And so this number here is always on the unit circle. And when alpha, the angle, is time depending, then this number here in the course of time is here rotating. We call it in German ein rotierender Zeiger. For some applications that is useful, and we have not referred to that so much, but nevertheless, I guess you have already heard about that. Good. Next thing is that I want to just here show that we can convert complex numbers from real part, imaginary part representation to this polar form using the Euler notation with the e power j angle. And yes, here with this representation, it's pretty easy to multiply two complex numbers because it's easily seen by multiplication. We will have to do what? We just have to multiply the absolute values, and we have also to multiply the exponential functions. However, as we know, e power j alpha 1 times e power j alpha 2, and we have to sum up the exponents, and then now you see, then we have just to sum up the angles. So multiplication in this form here is a pretty easy one. And whereas this real part, imaginary part representation is good for subtraction or addition, then we have to sum up the real parts and the imaginary parts, and that's it. I want you to keep something in mind when we have a complex number and we take the inverse. And then you see the following. Yes, then the absolute value is just obtained by taking the reciprocal value of the absolute value. So if that z absolute value is a 2, 1 over z has the absolute value 1/2. What is happening with the angle? Oh, the angle is just changing from plus to minus, or just changing its sign. That comes from the fact that 1 divided by e power x is nothing else than e power minus x. Good. Exponentialfunktion and logarithmus, I think we have already talked about that a little bit more in detail as it is done here, because we have investigated a logarithm table and stuff like that. So that is not that important for the future, but you should have this basic equations available. So, and what is also listed here in this script for the mathematical introduction is Laplace transformation. And there are also some rules given here, what we have not discussed so in detail. Laplace transform of the sum of two functions is the sum of the Laplace transforms. Yes, we immediately know that, therefore I have not referred to that in detail. Then the Laplace transform of a times f of t is a times Laplace transform of f of t. Then comes the important differentiation rule. And then here the integration rule. Integration is, of course, then corresponding to division by s. There is a small Laplace table added also here, and it's a little bit more than, oh my goodness, it's a little bit more than that what we, where is the table? Yes. It covers a little bit more than those things we have done. See, sigma of t 1 over s, that is something I told you to have in mind, e power minus at 1 divided by s plus a. Here is also listed the ramp. The sine and the cos we have also derived. And there is one thing what is here in addition, obtained 1 divided by s plus a. That was not obtained in our self-constructed table, what we did on the visualizer. And when we are facing this problem to transform that back, we have made partial fraction expansion. And then, yes, that has shown us somehow this typical curve charging a capacitor over a resistor. Yes, and so of course in many Laplace tables that is also listed here on the right side. Then comes something which seems to be very easy here on the right side. It's not that complicated, that thing here. And on the left side it gets complicated. So the complicated time functions here. And well, this is something we will treat later, but to just tell you now, there in the background is the step response of a second order low pass, which is an important thing on control theory, but we will come back to that later. So far we have not used that thing here, but we will have to use it later. So, and then come here some examples. Or first some Herleitungen, some rules which we derived here. This differentiation rule we did also Laplace transformation of the unit step, and here yes, there is also the exponential function shown, what we also have done, and so well that's it so far. And then some examples here. Oh, that is that famous low pass, where we found the step response. And, well, there is something more here which we have not done in our on our paper, on the visualizer, a second order differential equation. Oh, the input is 0, but then we have included initial conditions. Then it is shown how to solve that by including also the non-zero initial conditions here. So we will not go through that thing here. It would just be one more exercise for solving differential equation with Laplace transform. And as we are now in the future doing that quite often, I think we can skip that this example here. Good. Then, very important, the so-called Übertragungsfunktion, the transfer function, and you see, in general, such a differential equation may look like that. Oh, that's how it looks complicated. So you see, we do not have only the y of t, we have only also the first derivative with respect to time. It may also include the second derivative with respect to time, or the third, or may go up to the nth derivative with respect to time. And on the right side, there is the same structure. On the right side, there may not only appear an x, there may also appear derivative with respect to time of that x, and so on. So the structure on the right side may be like that. See, here I have listed a small example, that is that second order differential equation, and that also belongs to this family. Here the B0 is a 1, yes, and well, all the other coefficients are not there. So, and then here the A0 obviously is also a 1. The A1 is a 0, because the first derivative with respect to time does not exist here. But A2, that is t squared, and all the rest is also not there. And when we have such a thing, mathematicians or control engineers like that, because that can easily then be Laplace transformed. And so you see, if we have a second derivative with respect to time, we just write s square times y of s, applying the differentiation rule twice. Then we come to this formulation of the transfer function, and you see there's a polynomial in s in the numerator and a polynomial in s in the denominator. This is what we call the transfer function. And you should also keep in mind that we can convert this differential equation to the transfer function, and it also is possible to do that the way back, the inverse way. Once you have the transfer function, you can find the differential equation. You must just make this calculation beginning from here in the inverse direction, reverse direction, and then you will finally be able to, yes, if you have a transfer function, to also derive the corresponding differential equation. Here is in short words, characterized recipe for the solution with differential equations for the Laplace transformation. Now we need g of s. We make the Laplace transform of the input signal. We calculate y of s is g of s times x of s, and we make the inverse Laplace transform, if possible with a table. If not possible, well, we also have to use this partial fraction expansion method to split it up in simpler expressions. So that all does not tell you something new, because we have already talked about that stuff. And here we have also somehow mentioned that as g of j omega we can obtain by replacing s by j omega. And it says, well,
this here, it's stated,
the absolute value gives us the gain, or das Amplitudenverhältnis, and the phase shift. Well, what we have not discussed so far are Bode diagrams and Orts curve. Now I must ask you, have you ever heard Bode diagram? Answer me in the chat. By your microphone.
We did it during numerical programming, but we don't really understand it.
Okay, you did it, yes?
Yeah, using MATLAB, but that was, I think, last year. And we don't really understand the concept at all.
Okay, not understood.
Yeah, honestly,
okay. Okay, and we will have probably to discuss that here a little bit. Do you know about Orts curve? In English, it's Nyquist diagram, Nyquist plot. Keine Idee. Okay, good. So, and we will discuss that probably today, because we need those Bode diagrams and Orts curve. There is something perhaps I'm going to explain that on the visualizer, and then we can go back to to this chapter and take that as a repetition. Here is shown such an Orts curve, for example. There is also shown some Bode diagram. Where is it? That's the Bode diagram here. And of course we have to explain how that is constructed. Good. But before we are doing this, let me go back to our exercise. What you tried to solve. And here it's stated, find the gain and the phase shift for omega is equal to 1 over t, gain and phase, and so on. And for 3 frequencies. And that has something to do with our observation from our simulation in MATLAB Simulink. And let's see what is the result. So I have here uploaded some photos, and that is what I received via WhatsApp. And let me start with this solution. Let me do it like that. I think I can manage that somehow. Yes, I think like that. Yes. And then, yes. Okay. We take this one. Okay. 1 divided by 1 plus TS. Find the gain on the phase shift for omega is 1 over T. Gain is 0.707. This is correct. The phase is not correct. Yes. And find the gain on the phase shift for omega equal 10 over T. I think that is correct. And the phase shift is also correct. The next thing here, we find it for omega is 100 over T. The gain here is 0.57929. That's not correct. Because, yes, see, frequency is always increasing. 1 over T, 10 over T, 100 over T. And the gain is here reducing from 0.707 to 0.0995. And then, yes, should further decrease if we are coming here to even higher frequencies, because it's a low pass. The higher the frequency, the smaller must be the gain. And what is not correct here in the phase? That, yes, see, if here we have negative angles, well, we may assume that this was also here a negative angle, but the numerical value is also not okay. There is some calculation here. So 1 divided by 1 plus TS, yes? And then you replace that, and then that was that. Okay. Okay, absolute value is 1 divided by root 2. That is correct what you did here. And that, we must say, if we take the abs of this, then we have to take the absolute value of the numerator and divide it by the absolute value of the denominator. And 1 is the absolute value here. That is correct. And then we have root 2 here. Because 1 squared plus, and then the imaginary part squared is 1. And then 1 plus 1 is 2. And the root out of that is root 2. And that results in 0.707. It's correct. However, this next line is not correct. Here, you must say the angle of a fraction is what? Is the angle of the numerator minus the angle of the denominator. That comes from our, yes, as we have seen that before. If we multiply complex numbers, we have to sum up the angles. If we divide complex numbers, we have to subtract the angle. And the angle of the 1 here is 0. And the angle of 1 plus j is 45 degrees. And then it must be 0 minus 45 degrees. So indeed, here should come out minus 45 degrees. And then 100 over t. Yes, and I think that's now getting correct here. 1 divided by root. No. I think this one is belonging to omega is equal to 10 divided by t. Then this is correct. And this angle 10 and here you have done this 5.68 minus 90. Well, the result is correct. Yes, what comes out here. So it is approaching the minus, I think the minus 90 degrees. So, and then we did it once more. Okay, and then 100 here inserted, then I think you made an error here. Because that should be 1 over root of 100 times 100 plus 1. There is a 0 here missing. That must be 1001. Yes? And here I've only written 1001. No? Because 100 times 100 gives 10,000. No? And so there is a 0 missing here. That, yes, explains why that gets wrong here. But in principle, yes, you have been on a good way here. So let me just check the next thing. Here I take this one. Good. Looks good. I think that everything is correct. I'm not quite sure with that. It's at minus 85 degrees. But we can verify that pretty easily. So what is the, yes. Well, yes, no further explanation how to come to that, but I guess it's, yes. So in principle, it's okay, no? And now we take the next one. This is this. Yeah. So I guess here the phase minus 84 to the, so that is done nicely, yes. Seems to be good. And so I guess the student which we have discussed in the very beginning, I think here this thing here was a small error, because the student had what here, and the minus, no, I think it's correct, yes. So again, looking at that, yes, I would say, yes. Then the next thing is this. Phase. Okay. So I see what happens here. So I would, so probably the correct result comes out. But I would not do it like that, to make the conjugate complex here. To make the denominator purely real. Of course, it's an often used technique. However, it's time-consuming to do that. It's easier to then just take absolute value of the numerator divided by absolute value of the denominator, and for the angle, subtract just the angle of the numerator minus angle of the denominator. And then it is not necessary to make that calculation here, where you finally here get a 2 here and make the denominator purely real. Okay, but of course what comes out, root 2/2, seems to be correct here. And what else do we have here? I think here's something. Okay, 1 divided by root 2, 45. And there happened some small error here, because there is missing the minus. Phase shift is minus. And I don't think that this drawing here is correct. Because in this drawing here, it would indicate, hey, that thing here, the angle is plus 45 degrees. So something must have happened here. Yeah. I guess from here to there, must be has happened some small disaster from here to there. When I have a good interpretation of that, that means 1 divided by j plus 1, yes? And 1 divided by j is what? 1 divided by j is minus j. So I assume that here, from here to there, yes, that here happened, that error, that here this plus must be a minus. And keep in mind, 1 by j is minus j, what is easily verified. So now we have discussed that a little bit, your solutions, and just to give you this idea, 1 over j is, yes, if we expand that by j, then we have j here, and then here we have jj, and then jj is minus 1. Oh, and then comes easily out 1 over j is minus j. And then I guess that was the source of the error. Why then the angle has not got the correct sign. Good. Well, I think we don't have to, yes, do that anymore here. Gain is 1 divided by root 2, and the phase is minus 45 degrees. And here the gain is 1 divided by root 101, and the phase is, now I will, the phase is what? Well, take MATLAB, use it as a pocket calculator, and oh my goodness, I have here used that atom 2, and well, then what is happening here? Angle of the numerator is 0 minus, then I convert that to degrees, and yes, atom 2, and then I need a, as the imaginary part is a 10, and this should come out, minus 90? My goodness, what did I wrong? Here I must make a 1, minus 84, minus 84.3. So this is a value which I have not in mind. And again, just doing that for even higher frequencies, and we have to take the 100 here, and then is minus 89, 1427, 3, and 1 divided by root, and what was that? The imaginary part is 10 to the power of 4, 1 0, 2 0, 3 zeros, and the measure must be 1 more 0. However, now I must insert a 1 here. And believe me, if you take that, for example, 1 divided by 2RT divided by 1 divided by SQRT 101, what comes out? 0.0995. And look at the visualizer. What we have read in MATLAB Simulink, 0.0955. With a phase shift, we have a little bit of problem to have a proper reading of that. Thus, we estimated it's minus 90 degrees, and the true and correct value would now be yes, minus 84.3 approximately. And what we have not measured in our MATLAB Simulink stuff, that is this, and that is for omega equal 100. But we have calculated here in our exercise what comes out here. And important is, as you see, the gain is permanently reducing the higher the frequency is. And therefore, that is clear. That is a low pass. And I could also ask you, hey, what is the gain for frequency 0? I have not asked here. But if I would have asked, you would have replaced the omega by 0. and do that here. Replace S by J omega, that omega to 0, and then you will see a 1 comes out. So the gain for frequency 0, that's the lowest frequency we can imagine. There the gain is 1, and that says low frequencies are passing, high frequencies are not that good passing. And that is where the name low pass comes from. Good. Now we have finished that exercise. Well, the question is if you need one more exercise. Well, we will do it. Some exercise in complex numbers. Exercise and complex numbers. And wir formulieren es schon. Wie groß ist der Betrag und der Winkel von A plus J, B, J, C minus 1 und D, J, 1 plus J dividiert durch 1 minus. So, und dann haben wir noch eine zweite Aufgabe. Und die zweite Aufgabe, berechnen Sie Real- und Imaginärteil von, und das kommt A, E hoch J, Pi halbe. Ich mache das jetzt im Bogenmaß. Ne? Ich könnte das auch E hoch J 90 Grad schreiben. Ja? Aber jetzt machen wir es mal so. Ja? B 4 mal E hoch J 3 Viertel Pi. Oh je. Dann C E hoch J 5 halbe Pi und D ja, minus 2 mal E hoch J 3 Viertel Pi. So. Und das ist etwas, das sollte man eigentlich ohne Taschenrechner auch hinbekommen. Ja? Und ich würde sagen, nehmen Sie sich jetzt mal 10 Minuten Zeit, versuchen Sie, diese Aufgabe zu lösen und wir gehen das dann nachher zusammen durch und versuchen dann zusammen einen schnellen Weg zu finden, um diese Fragen zu beantworten. Und wir werden versuchen, auf einen Taschenrechner zu verzichten und wir wollen auch das MATLAB nicht nehmen, sondern man müsste eigentlich in der Lage sein, das auf dem Blatt Papier zu machen. So, und dann würde ich sagen 10 Minuten und ich melde mich dann in 10 Minuten wieder und dann diskutieren wir über die Lösung. So, also dann viel Spaß damit. Wir sehen uns dann in 10 Minuten wieder. So, ja, ich bin wieder zurück und ich denke, es war nicht allzu schwierig. Ja, und wir lösen das jetzt auch zusammen sehr schnell. Ja, und mir hilft das immer, wenn ich mir das in der komplexen Ebene vorstelle. Ja, ja, also ich mache deshalb hier mal ein Achsenkreuz dahin, Realteil hier auf der horizontalen Achse, Imaginärteil auf der vertikalen Achse. Und wo ist 1 plus j? Das mache ich mal hier eine 1 hin, der Imaginärteil 1 auch hier. Und dann ist 1 plus j ist dann hier. Ne? So, und wie lang ist der Pfeil? Naja, Pythagoras 1 im Quadrat plus 1 im Quadrat, die Wurzel draus, also 1 plus j und der Betrag ist Wurzel aus 2. Und der Winkel, da sieht man unschwer, ist 45 Grad. Also Winkel von 1 plus j ist 45 Grad. Oder, wenn Sie so wollen, Pi Viertel. So, jetzt wo ist die Zahl j? Und die Zahl j ist natürlich dann diese Linie hier. Ja? Also das hier ist 1 plus j und das hier ist j. So, und dann sieht man natürlich sofort, Betrag von j ist 1. Ja? Und der Winkel von j ist was? Ist 90 Grad. So, minus 1. Wo ist minus 1? Minus 1 liegt hier. Wie groß ist der Betrag von minus 1? Naja, das ist trivial, das ist 1. Und wie groß ist der Winkel von minus 1? Das ist 180 Grad. Es wäre auch nicht schlimm, wenn wir dann sagen würden, minus 180 Grad, entweder plus oder minus, doesn't matter. So, wie machen wir das? Da würde ich Folgendes vorschlagen, 1 plus j dividiert durch 1 minus j. Ich würde nicht konjugiert komplex erweitern. I would not do it with conjugate complex expanding that thing here. Ich würde einfach sagen, das ist der Betrag vom Zähler. Und der Betrag vom Zähler ist ja Wurzel 2. Und der Betrag vom Nenner ist auch Wurzel 2. Ja, weil wir ja den Imaginärteil quadrieren müssen. Der Imaginärteil ist aber minus 1. Und wenn man das quadriert, dann kommt natürlich auch wieder 1 raus. Und dann ist also der Betrag gleich 1. Und wie groß ist der Winkel von 1 plus j? Dividiert durch 1 minus j. Das ist der Winkel vom Zähler. Das sind 45 Grad. Das haben wir ja schon gehabt. Und dann minus der Winkel vom Nenner. Und wo ist das 1 minus j? 1 minus j ist da. Ne? Das wäre also 1 minus j. Und deshalb ist der Winkel minus 45 Grad. Ja, den muss ich aber subtrahieren. Und dann habe ich minus 45 45 minus 45, das sind dann 90 Grad. Ja. Ja. Natürlich hätten Sie das auch mit konjugiert komplexem Erweitern herausfinden können. Ja. Aber so geht es, glaube ich, einfacher. So, berechnen Sie Real- und Imaginärteil von. Ne? Also der Realteil von e hoch j Pi halbe, der ist, so, ich mache wieder so eine Zeichnung, wo ist e hoch j Pi halbe, also das hat den Betrag 1, ne? Hier, alles was e hoch j irgendwie ist ja auf dem Einheitskreis, also ist nur die Frage, naja, wo denn auf dem Einheitskreis? Und weil der Winkel Pi halbe ist, ist das jetzt natürlich die komplexe Zahl j. Ne? Im Prinzip ist das gerade das Umgekehrte wie das da oben. Ja? Ja? Und deshalb, wenn wir sagen, der Realteil ist 0 und der Imaginärteil von E hoch JP halbe ist 1. Gut. 4.
時間は咧，舒服嘅。係啊，我會覺得啲問題攞翻上自己冇所謂，然後一個小時啊。誒，喺個書房去教我